Welcome back everybody to MIE 270. This is tutorial number 3 where we'll be discussing the magnetic properties of materials. Let's begin with problem number 1. Problem number 1 reads, a coil of wire 0.2 meters long and having 400 turns carries a current of 10 amps. A. What is the magnitude of the magnetic field strength? B. Compute the flux density if the coil is in a vacuum. C. Compute the flux density inside the bar if titanium is positioned within the coil. And D. Compute the magnitude of magnetization. So let's begin with part A. Part A asks us to find the magnitude of the magnetic field strength. And we know that the magnetic field strength, or designated by H, is a function of the number of turns within the coil times the current within the wire divided by the length of the wire. So all we need to do is substitute the values that are given to us in the problem, and that's going to yield us our magnetic field strength. So we can say that 400 turns multiplied by 10 amps divided by the length of 0.2 meters is going to yield us a value of 10,000 amps turns per meter. And that's the value of our magnetic field strength. Now part B wants us to compute the flux density if the coil is in a vacuum. So our flux density within a vacuum, designated by B naught, is equal to mu naught times H, where mu naught is the permeability within a vacuum and it's just a constant. So we can substitute the constant of 4 pi times 10 to the minus 7, and the units are henries per meter, and multiply that by our 10,000 amps turns per meter, which is our magnetic field strength, and that's going to give us a flux density of 1.257 times 10 to the minus 2, and the unit is Teslas. Now part C wants us to compute the flux density inside the bar if titanium is positioned within the coil. So our flux density within the bar is equal to B is equal to the permeability within a vacuum times the magnetic field strength plus the permeability in a vacuum times the magnetization. However, the problem doesn't give us the magnetization. So what we can do is substitute the magnetization for the following. Mu naught times H plus mu naught times chi m H, where chi m is the susceptibility of the material to magnetization. And we're just going to read that from the table. So the susceptibility for titanium is 1.81 times 10 to the minus 4. So let's manipulate this equation a little bit further, and we say that mu naught times H is times 1 plus chi m. So substituting our values of 4 pi times 10 to the minus 7 henries per meter times 10,000 amps turns per meter, and multiply that by 1 plus chi m, which is 1.81 times 10 to the minus 4. And that's going to yield us a value for the flux density of 1.257 times 10 to the minus 2, and again the unit is Teslas. And the final thing we need to do in part D is compute the magnitude of magnetization. Now in part C, we manipulated the equation so we didn't have the magnetization, and now we're going to do the following to solve for it. So we can say that the magnetization M is equal to chi m times H, where chi m again is the susceptibility of the material to magnetization, and we're going to read that from the table. So we can say that 1.81 times 10 to the minus 4 multiplied by our magnetic field strength, which is 10,000 amps turns per meter, and that's going to give us a value of 1.82 amps per meter. And that's the conclusion to problem number 1. Let's move on to problem number 2. Problem number 2 says the chemical formula for manganese ferrite may be written as follows. Because there are 8 formula units per unit cell, if this material has a saturation magnetization of 5.6 times 10 to the 5 amps per meter and a density of 5 grams per cubic centimeter, estimate the number of Bohr magnetons associated with each manganese ion. Note that the molecular weight of the manganese ferrite is 230.64 grams per mole. So we know that our magnetization saturation, designated by M sub S, is equal to NB mu B times N, where NB is the number of Bohr magnetons mu B is Bohr magnetons, and N is equal to rho, which is the density, times Na, which is Avogadro's number, divided by A, which is the molecular weight. So essentially, N is the number of manganese ions per cubic meter of material. So if we combine these two equations and isolate for what we need to find, which is Nb, the number of Bohr magnetons, and substitute our values, we'll get the result. So let's combine the two equations and isolate for Nb. So Nb, or the number of Bohr magnetons, is equal to Ms, which is our magnetization saturation, times our molecular weight, divided by mu B, which is Bohr magnetons, times density, times Avogadro's number. Now all we need to do is substitute our values. So our magnetization saturation is 5.6 times 10 to the 5 amps per meter, times 230.64 grams per mole, which is our molecular weight, divided by mu B, which is a constant of 9.27 times 10 to the minus 24, and the units for that is amps, meters squared, divided by Bohr magnetons, times our density, which is 5 grams per cubic centimeter, and finally multiplied by our Avogadro's number, which is 6.022 times 10 to the 23, and the unit is ions per mole. Now, if you plug all those values into your calculator, you're going to get a number of Bohr magnetons, which is equal to 4.6, and the units we can say is Bohr magnetons divided by Mn2 plus ions. And that's how you solve problem number 2. Let's move on to problem number 3. Problem number 3 reads, a flux density versus magnetic field strength graph is plotted below for a plain carbon steel alloy. A, what are the values of the initial permeability and initial relative permeability? B, what are the values of the maximum permeability? C, at about what magnetic field strength does the maximum permeability occur? And D, to what magnetic susceptibility does the maximum permeability correspond? So this is a very fundamental problem. We're given a flux density versus magnetic field strength curve or graph, and we're asked to analyze it. So the first thing they want us to do is determine the initial permeability and the initial relative permeability. So we need to do the initial permeability first because we can get that from the graph. So the initial relative permeability corresponds to the slope of the initial linear portion of the curve. So right down here where I drew this line, we can say the slope of that is equal to our initial permeability. So mu I, which is our initial permeability, we can say is equal to the change in flux density divided by the change in magnetic field strength. So I'm going to use the values that I chose in the tutorial solutions just so we can keep consistency. So the values I chose were 0.0225 minus 0, and that's Teslas, divided by 56 minus 0, and the units for that are amps per meter. So I decided to choose the origin because it's just a clean value of 0, which will make our answer a little bit nicer. So we can say that our initial permeability, mu I, is equal to 4.0 times 10 to the minus 4 henries per meter. So that's our initial permeability. Now it asks us to also find the initial relative permeability. And we know that the relative permeability is just the ratio of our permeability divided by our permeability in vacuum. So mu R is equal to mu I divided by mu naught, which is equal to 4.0 times 10 to the minus 4 henries per meter divided by 4 pi times 10 to the minus 7 henries per meter. Plugging that into your calculator is going to lead you a value for the initial relative permeability of 318.22. And note that we don't have any units on that because, again, we said it was a ratio. Let's move on to part B. Part B, what is the value of the maximum permeability? So the way we're going to get our maximum permeability is we're going to take the tangent to the point on this curve that yields the greatest slope. So we're going to need to take a point within this region that's going to give us the greatest slope. So let's just take this point for right here, for instance, and draw the slope to that point. And we can say that that slope is going to be our maximum permeability. So we can say that mu max is equal to the change in flux density divided by the change in magnetic field strength. That's going to yield the greatest slope. So the points that I chose were 1.3 minus 0.1 Teslas divided by 81.25 minus 59.7, and that's amps per meter. Plugging that in your calculator is going to give you mu max, which is equal to 5.49 times 10 to the minus 2 henries per meter. And that's going to be our maximum permeability. Now, part C says, to what magnetic field strength does the maximum permeability occur? So the point that we drew our tangent to, we're going to come straight down, and that's going to give us a value of 68.25 amps per meter. So that's the value to where our maximum permeability occurs. And the final thing we need to do is part D. Part D says, to what magnetic susceptibility does the maximum permeability correspond? So we know that our maximum susceptibility, or chi max, is equal to our maximum relative permeability minus 1. But we don't have a relative permeability at our maximum. We only have the initial relative permeability. So what we need to do is manipulate this equation to get rid of it and implement something that we know. So let's say that chi max is equal to our maximum permeability divided by the permeability in a vacuum minus 1. So now we can simply substitute our values and solve. So chi max is equal to 5.49 times 10 to the minus 2 henries per meter divided by 4 pi times 10 to the minus 7 henries per meter minus 1. And that's going to give us a maximum susceptibility of 4.37 times 10 to the minus 3. And that's how we're going to conclude problem number 3. Let's move on to problem number 4. Problem number 4 says a coil of wire 0.5 meters long and having 20 turns is carrying a current of 1 amp. Part A says compute the flux density if the coil is in a vacuum. B, a bar of an iron silicon alloy, the BH behavior for which is shown below, is positioned within the coil. What is the flux density within the bar? And C says, suppose that the bar molybdenum is now situated within the coil. What current must be used to produce the same flux density in the molybdenum as was produced for the iron silicon alloy in part B using 1 amp? So let's begin with part A. Part A wants us to calculate the flux density within the coil if it's situated in a vacuum. So this is similar to what we did in the first problem, where we can say that the flux density is equal to mu naught, which is the permeability in a vacuum, times H, which is our magnetic field strength. So we don't have a magnetic field strength, so we need to substitute for mu naught times our number of turns times our current within the wire divided by our length of the wire. Now simply substituting our values of 4 pi times 10 to the minus 7 henries per meter times 20 turns times 1 amp divided by 0.5 meters. Plugging all that in is going to give us a flux density of 5.28 times 10 to the minus 5 Teslas. So that's all we have to do for part A. Now part B says a bar of an iron silicon alloy, which BH behavior is shown, is positioned within the coil. What is the flux density of the bar? So the first thing that we need to do is determine the magnetic field strength. So H is equal to the number of turns times our current divided by our length. And that's going to be 20 turns times 1 amp divided by 0.5 meters. And that's going to give us a magnetic field strength of 40 amps turns per meter. So now all we have to do is go to our 40 on our graph and go all the way up until our point of intersection of the curve and come across and read our flux density, which is approximately 1.3. So we can say that our flux density is equal to 1.3 Teslas for part B. And finally, part C says, suppose that the bar of molybdenum is situated within the coil. What current must be used to produce the same flux density in the molybdenum as was produced in the iron silicon alloy in part B using 1 amp? So what we have to do first is calculate our magnetic field strength. So H is equal to our flux density divided by our permeability. However, we're not given the permeability. So we can manipulate this equation by saying this is equal to our flux density divided by our permeability in a vacuum times our relative permeability. And again, we're still not given the relative permeability, so we have to do one further manipulation by saying this is all equal to our flux density divided by our permeability in a vacuum times 1 plus chi m, which is our susceptibility for our material, which is given in the problem. So now we can simply substitute our values and we'll get that our magnetic field strength is equal to our flux density, which is 1.3 Tesla, because we want it to be the same from part B, divided by 4 pi times 10 to the minus 7 henries per meter times 1 plus chi m, which is our susceptibility for our material, which is 1.19 times 10 to the minus 4 for molybdenum, and then that's going to give us a value of 1.03 times 10 to the 6 amps turns per meter. Now the final thing we need to do is calculate our current. So we know that our magnetic field strength is equal to the number of turns times our current divided by our length. So rearranging for our current, we get that our current is equal to our magnetic field strength times our length divided by the number of turns. And then we can say that 1.03 times 10 to the 6 amps turns per meter times our length, which is still 0.5 meters, and divide that all by 20 turns. So plugging that into your calculator is going to give you a value for your current, which is equal to 25,750 amps. And that's the final answer to part C, and that concludes problem number 4. Let's move on to problem number 5, which is our final problem in magnetic properties of materials. So the flux density versus magnetic field strength graph is plotted below for a nickel iron alloy. A, what is the saturation flux density? B, what is the saturation magnetization? C, what is the remanence? D, what is the coercivity? And E, on the basis of the data in the tables below, would you classify this material as a soft or hard magnetic material? Why? So we'll save part E for later as I switch the slides. But for now, let's start with A. So A says, what is the saturation flux density? So looking at this typical BH curve, we can see that our material becomes saturated here at this point. So if we take this and come all the way across, we can say that our saturation flux density, BS, is equal to approximately 1.5 Teslas. So we can say that BS is equal to 1.5 Tesla. And that'll be the answer to part A. Part B says, what is the saturation magnetization? So we know that our saturation magnetization is just equal to our flux density magnetization divided by mu naught, which is our permeability in a vacuum. So we can say that that's 1.5 Tesla divided by 4 pi times 10 to the minus 7 henries per meter. And that's going to give us a magnetization saturation of 1.19 times 10 to the 6 amps per meter. So that's the answer to part B. Now let's move on to part C. Part C says, what is the remanence? So the remanence is our intersection point on the B axis of our curve. So at this point right here, which is our intersection, we can say is our remanence. And that could be approximated at 1.47 Tesla. So we can say that our remanence is equal to 1.47 teslas. And part D says, what is the coercivity? So the coercivity corresponds to our intersection on the h-axis of the curve, which is right here. So we can say that is our coercivity, which is approximately 17 amps per meter. So we can say that our coercivity is equal to 17 amps per meter. So now finally, part E says, on the basis of the data in the tables below, would you classify this material as a soft or hard magnetic material and explain why? So let me go to the next slide, which is our table. So our first table is on hard magnetic materials and our bottom table is soft magnetic materials. And the only way we're able to determine which our material is by justifying our saturation flux density, our remanence, and our coercivity, at which we previously calculated based off of the BH curve. So let's start with our saturation flux density. So our saturation flux density can be found on the second table on soft magnetic materials. And we can see that 1.5 Tesla is well within the range, which is situated down here for soft magnetic materials. So we can put a check mark here next to soft magnetic materials for saturation flux density. The second thing we need to look at is our remanence. And our remanence can be found up here in hard magnetic materials. And now we can see that 1.47 is fairly close to the values at which we're seeing here for hard magnetic materials. So we can put a check mark beside our hard magnetic materials for our remanence. So now we're tied. We have one positive going towards our hard and one positive going towards our soft. So we need the tiebreaker. And the only thing that we have left is our coercivity. So our coercivity can be found again up here for hard magnetic materials. And we can see that the values in this table are significantly greater than our value of 17. So we can put an X beside the coercivity corresponding to hard magnetic materials. And on the basis of the information that's given to us, we can say that our material is a soft magnetic material. So that's going to conclude for problem number 5, and that'll also conclude our section on the magnetic properties of materials.